I found the single slowest x86 instruction, and it takes 62 seconds to finish executing. Hardware researchers have spent decades optimizing processor pipelines. We build complex branch predictors and out-of-order execution engines to ensure that every cycle counts. But what happens when you deliberately strip away all those optimizations? A new project called CPU Deoptimization aims to answer that exact question. The goal is simple but brutal. Find the single slowest x86 instruction that can execute in isolation. No cache hits to speed things up. No bus contention to slow things down. Just pure, unadulterated latency from start to finish. The researcher has created a hall of shame to document these performance disasters. One instruction stands out as the absolute worst offender. It takes 198 billion cycles to complete. That is not a typo. That is 198 billion cycles spanning 62 seconds of wall clock time. We are talking about a full minute of the processor doing absolutely nothing, but processing one tiny piece of data. It is a fascinating look at the hidden costs of legacy architecture. To get these numbers, the researcher had to be extremely careful with the testing environment. The standard approach of just running a benchmark loop doesn't work because the CPU cache will speed things up on the second iteration. So the team had to find a memory region with the absolute highest latency they could find. They essentially starved the connection to the rest of the system. They induced a specific type of contention by targeting the bus that transfers data from the CPU to other parts of the system. This is not contention on a lock or the memory address itself. It is contention on the physical connection. The instruction performed a massive read operation over the PCI bus rather than the faster PCIe bus. Since PCI is basically direct memory access, the device has some memory that appears as part of the host CPU memory space. By forcing the CPU to fetch data from that high latency region, they ensured that the instruction would take as long as physically possible to complete. The current champion of the Hall of Shame is the FXR-Store64 instruction. This instruction is responsible for loading a 512-byte XMM state from memory back into the processor registers. For those who do not know, XMM registers are used to store floating-point data and SIMD operations. Loading that much data is heavy enough on its own, but when you combine it with the high-latency memory region, the numbers explode. The instruction has to parse the entire 512 bytes and restore the state of the floating point unit. The researcher confirmed that this specific instruction was the one that broke the scale. It is a legacy instruction from the x87 floating point unit. The x87 unit is obsolete and was succeeded by SSC and SSC2 instructions. This means it is not really used anymore in routine modern software, but because it still exists, it still has to work, and it still has to pay the cost of its history. You might be wondering why we should care about an instruction that takes 62 seconds to run. The answer is compatibility. Even though modern compilers do not normally generate these slow instructions anymore, older software can still use them. If you have a legacy application that relies on specific bit compatibility with the x87 floating point unit, you are stuck with its quirks. One commenter pointed out that porting logic to ARM that relies on being bit compatible with x87 has been the bane of their existence for the past year. This highlights a real problem. As we move to different architectures, we lose the subtle behaviors of the old hardware. The FXR-Store64 instruction is a perfect example of a feature that was useful in its day, but has become a performance liability. It is a reminder that every instruction in the x86 instruction set carries the weight of decades of design decisions. The community reaction to this project has been a mix of awe and confusion. Many people are still not clear why that instruction takes so long even without contention. One user asked if the slowness was due to the PCI bus transfer limits. The answer is yes. The PCI bus is significantly slower than PCIe. When you do a massive read operation over PCI, you are bottlenecked by the bus width and clock speed. Another commenter noted that the researcher induced contention by targeting the bus that transfers data from the CPU to other parts of the system. This is a crucial distinction. It is not about the instruction itself being inherently slow. It is about the environment in which it runs. The instruction is slow because it forces the CPU to wait for data that is far away and hard to reach. This is a valuable lesson for anyone who writes low-level code. You cannot just look at the instruction latency in isolation. You have to look at the memory hierarchy and the bus topology. So what can we take away from this? First, cache locality matters more than you think. If you can keep your data close to the processor, you can avoid these massive latency penalties. Second, legacy instructions have costs. Just because an instruction is obsolete does not mean it is free. It still consumes power and time when it is used. Third, understand your hardware. The FXR Store 64 instruction is a relic of the x87 floating point unit. It is a reminder that the x86 architecture is a palimpsest of decades of design choices. Every new layer is built on top of the old ones. This project is a fun way to explore those layers. It shows us what happens when we push the boundaries of the hardware. It is a celebration of the complexity of modern processors, and it is a warning to those of us who write code that runs on them. The CPU Deoptimization project is open source and available for anyone to explore. The researcher has created a hall of shame that documents the worst offenders. There are likely many more instructions that could be tested in different environments. I encourage you to check out the repository and see what other slow instructions you can find. The project is a great example of how tinkering with hardware can lead to surprising insights. It is a reminder that even in the age of terahertz processors, there are still mysteries to be solved. Thank you for watching. If you enjoyed this deep dive into the slowest instruction, please like and subscribe. I will see you in the next one. If you enjoyed this deep dive into the slowest instruction, please like and subscribe. I will see you in the next one.